Hello everyone, and welcome to a discussion of work done by variable forces. But before we get into work done by variable forces, let's review what we already know about work. Here's an example of a box that's being pulled at an angle theta by an applied force F of A through a distance d at a constant velocity. Our system here would be the box and the Earth, which of course is not isolated as that applied force clearly pierces the system boundary. Something is applying this force, it's just not something that we know about. So let's draw a quick force diagram. Here is our applied force at an angle theta, which we can of course break up into F of AX and F of AY. We have an upward support force or normal force, a downward force of gravity, which must balance the F of N and F of AY. And then we have a force of kinetic friction, which must balance F of AX, as it is an accelerating in any direction. So, what force actually pulls the box across the floor? It's not the entire F of A, right? Because some of F of A, F of AY, is going into balancing out the vertical forces. So it's really only F of AX. F of AX is, of course, constant and positive. So if we were to graph that force, and notice here, that's the external force as a function of position. It's not a time graph. It's force as a function of position. It would be a horizontal line at F of AX. And therefore, that external force will do work. It will transfer energy, in this case, into the system by means of the external force, F of AX. And as we've defined before, it is the area under the external force versus position graph. Right, so it's the area underneath. So if we allow the thing to be pulled a distance d, it's that area. That area, of course, has a area of length times width, or F of AX times d. F of AX could be written as F of A cosine of theta, and we get our normal work math model. And this is, of course, for a constant force. So now let's get to the task at hand, which is what happens if that force isn't such a nice constant force? Well, here is a case where the force is not constant, although it is the next best thing, which is linear. So if we make this graph, I want to know if this is the force. So the force as a function of position is 3x plus 2. Notice this is not a time. This is a function of position, where force is in newtons. How much work is done in moving the box from 1 meter to 3 meters? It's a one-dimensional case, so we're really moving it a total of 2 meters. So here's the graph. Let's make the graph. This is a graph of, linear graph, of slope 3 with y-intercept 2. So it would look like this. And the work would simply be the area under the curve from 1 to 3 meters. Now, a couple different ways we could write that. Of course, the calculus-y way is to take the area from 0 to 3, which is that big area. And notice I've broken it up into a big rectangle and a big triangle. And then subtract off the area from 0 to 1. And what's left is the area in between, or the total amount of energy transferred, the amount of work done. So there's those two shapes. This is the one from 0 to 3, and this is from 0 to 1. If you need to pause here and check that out, you can, but it's basically rectangles plus triangles in each case. And if you work it through, you get a nice round 16 joules. Notice that it is positive, which means we are adding energy in to the box Earth system. So this is kind of the way to grind through it, all right, by using the graph. But what if you don't want to use the graph? You don't have to. You could use calculus. If work is the area under the curve of the external force versus displacement, then in calculus speak, work is the integral of the force with respect to position from 1 to 3 meters. Notice this is force as a function of position, not force as a function of time. Very important that you get what we're integrating over, which is why it's not a trivial thing here with this dx, right? It's not a dt, it's a dx. Well, the function is simply 3x plus 2. Hopefully you can do this integral. Use the power rule, add 1 to the exponent, divide by the exponent. So 3x becomes 3 halves x squared. 2 is just 2x. It's the integral of a constant. And now we have to evaluate it. Evaluating it at the big triangle and square, or rectangle, sorry, is from 0 to 3. That's evaluating it at 3. Minus, subtract off the little one from 0 to 1. And that's what we're doing here. Remember, that's what it means. It literally means what we just graphed a moment ago. And of course, if you work this through, you will get the exact same positive 16 joules. Now, personally, I find this easier once you understand how to do integrals. And again, one thing that I want to emphasize here is that work is the area under the graph of external force versus displacement or position. It is not a time graph. So be careful there. Second example, a three-dimensional unit vector notation problem. So here we have a force acting upon a box given by this function. Notice we've broken down into I cap, j cap, and k cap parts. And in 3 dimensions, the object is moving from an initial position of 2 I cap plus 3 j cap minus 1 k cap to a final position of negative 4 I cap plus 2 j cap plus 3 k cap. Remember that r is position vector. Now, this would be really hard to do graphically and really hard to even draw out so that you could visualize this, because this is really moving in 3 dimensions. The calculus, however, won't lead you wrong. In 3 dimensions, we can say that work is the integral of f dotted with dr. If you remember, we said it was f dot d in 3 dimensions for constant forces. So for variable forces, it's the integral of f dotted with dr. Now, plug in our two functions, our force function and our displacement function. And notice here I'm writing it in vector notation, in unit vector notation, but I'm also writing it out symbolically. We'll throw in the actual things here later. And we've done a 3 by 3 dot product. In fact, you proved what a 3 by 3 dot product is. It's this. The x times the x plus the y times the y plus the z times the z components. If you don't believe me, go back a couple of worksheets and check this out. You've proved that already, so we can use it. And since this is the integral of a sum, it is simply the sum of the integrals. Now, in this case, nothing cancels out, right? Because we have x, y, and z in all cases. This could be simpler, of course, if you only have 1 or 2-dimensional cases. But this is really the more complex 3-dimensional case. So, using this, we can now plug in the functions. And notice what I did here. I took the x part of the force here, the y part of the force there, carried the negative sign along, and the z part here. And then notice my limits of integration came from my initial to my final. My x, I started at 2 and I ended at negative 4. My y, I started at 3 and ended at positive 2. And my z, I started at negative 1 and ended at 3. So take a second here and notice how I mapped all this from the original statement, because that's not a trivial thing. The rest of the problem really isn't that bad once you get this part written out. We notice here that we're taking integrals of different variables, so you've got to be a little careful. So first of all, we have the integral of 4x dx. So that would be add 1 to the exponent, divide 1 by the exponent, right, which would be 2x squared. Here we have 2y dy. Add 1 to the exponent, divide by the new exponent. 2 over 2 is 1. And over here we have the integral of a constant, dz, so it's just 5z. Again, notice you got to be a little careful here about these dx, dy, and dz's, because that's what you're integrating over. So that's the variable that pops up when you do the integral. And now we just have to evaluate upper limit minus the lower limit. So here's 2x squared evaluated at negative 4 minus 2x squared evaluated at 2, and so on. Work through all of these, and you get 24 minus a negative 5 plus 20, which is a grand total of a positive 49 joules. So in moving the thing from this position to this position using this force in 3 dimensions, we get a scalar answer. It's kind of cool, really, in the end, that you just get one number out. This is how much energy we added into the box Earth system in this case, applying this variable force in 3 dimensions from here to here. So I'm going to give you some problems to do on the next worksheet that you'll do tomorrow that will, give you some more examples of this. Maybe not as complex as this, but, at least a couple of dimensions, 1 or 2 dimensions. So I hope you enjoyed this little discussion of work done by a variable force.